Hello everyone. I know it's last talk before lunch, so I'll try to be quick. And it will be even quicker if you have no question at all. So I'm going to present a structure motion pipeline with design based on AV1. But first of all, a bit about myself. So my name is Julien. I'm a PhD student and research assistant at Trinity College, Dublin, under supervision of Professor Anil Kokram. Probably many of you know him. I'm also a researcher at KBER, real-time video interaction company. JD talked about it a little. I used to work for Shadow, cloud gaming company based in France, and I've joined Videolan 3 years ago, I think, something like that. My work is mainly focused on real-time video processing and how to optimize this processing by using available features from encoded bit streams. Basically, if we talk about AV1, that's the kind of features you could find. And the one I'm mostly working with right now are the blocks, motion vectors, and reference frames. So if you take a random frame, you have coding blocks. Amazing. And for those blocks, most of them, you have motion vectors and a reference frame. Basically, it tells you that blocks come from that location in that frame that you already processed. Really simple idea. And seeing that, we thought that we could reuse them for getting motion fields. So on the left, you have the processed motion fields extracted directly out of AV1 bitstream. And on the right, you have the ground truth optical flow. So you can see that processed motion field out of AV1 is really, really close to the ground truth optical flow, telling you how good motion vectors in AV1 can be. We published a paper to Picture Coding Symposium that happened in December with a bit more details than just, look, it looks very similar, so it works. We do compare AV1 with HTVC in terms of quality of motion vectors and some presets for AV1. We mainly use LibAOM and NVEnc AV1 for this work. And now we are looking for another application. What can we do with those motion vectors? What could we accelerate? And we got the idea of using them for structure for motion. So the idea behind structure for motion is really, really simple. You have multiple 2D view of the same objects, and by tracking key points, so points of interest, you can reconstruct the objects in a 3D point cloud. So that's a really classical pipeline for structure for motion. So on the left, you have the inputs, the frames, the correspondence search, which is the key point extraction, key point matching, and the incremental reconstruction. So as I said, for the correspondence search, you basically find points of interest in your image, and you try to match them between all images in order to get multiple points of view of that specific point, so you can get the 3D position. Our goal is to replace those two first processing bits. Why? Because it's always really time consuming and it uses a lot of computing power. So first part, the key point themselves. So you have an image with 6 key points on the left, and on the right you have corresponding block decomposition. The thing that you should see, I hope, is that where you have 6 key points, you also have really small blocks. So it seems to fit quite well. And then for the matching, really easy, motion vectors. Issue is motion vectors does not always represent the real motion in the video. Sometimes it will give you a block which is close enough for the encoder to reuse. So we need to prune out those bad motions. In order to have something really efficient, we do not want to process our RGB data. If we can just stick to motion vectors, it will be better for us. So we came with a simple idea. Since it's a video, high frame rates, motion vectors should be really close one to another. So by just doing a really simple similarity test, you can print out bad motion vectors. So in this case, we just use cosine similarity. So basically, when two vectors have the same direction, cosine similarity is equal to 1, 0 when they are perpendicular, and the opposite is -1. So in this case, we want motion vectors to be above, like the cosine similarity to be above 0.95. So really close one to another. That's the global pipeline. Not an amazing chart, but well. First part is encoding the video. Important thing, we do not want to reinvent everything. So we are reusing CallMap, which is more or less state-of-the-art structure for motion tool. So most of the industry is using CallMap for reconstructing 3D point clouds. So we just wanted to integrate our work into CallMap directly. So as I said, first step is to encode the video, import everything into CallMap. That's not really important. Extract the metadata. So to do that, right now we are using AOM inspect tool. And then it's more or less what I explained earlier. Getting the block, the motion vectors, the reference, and making it work. There's something you could see here, which is generate tracks. So basically, you have more or less two big ways to do structure for motion for the matching. Something called exhaustive matching, where you try to find matches between all the key points and all the frames available. Something called sequential matching. We just check last two frames. Sequential matching is faster, but really bad. Quality is not that great. With motion vectors, you do not have, you cannot say, okay, this block is from that frame, that frame, that frame. That's not something available. So what we are trying to do is to say, okay, this block comes from here, that location is also linked to that place. So we try to create a track to say, okay, that block is visible in all those frames. Once we got all those tracks, that's when we apply the cosine similarity test. And then it's just CallMap incremental mapping. Okay, here it is. So the video was taken with my phone. I was in the tramway going to Video Labs offices in Paris, and I got the idea, like, what happened if I just record through the window? So amazing video, amazing reconstruction, seems to be correct, but hard to tell like that. So, oops. We decided to compare it with three other existing pipeline. So top right is the classic one, sieve key points and exhaustive matching. On the bottom, we have two deep learning techniques. One called DISC for the key point detection and light glue for matching, and superpoint and superglue. First thing we could tell is that we have way more 3D points than any other solutions. Why? Because we use all the coding blocks available. We do not try to get only good points to reduce the computation. If you do something like sieve plus exhaustive matching, and the more points you add, the more expensive it will be. In our case, we don't have that issue. And something really interesting, since we have more points, the precision of the reconstruction seems to be also better. So in this case, it's a Paris street sign, and you can see that you have a better idea of the shape of that sign with our pipeline, which is in the middle, than the classical one, which is on the left. So to give just a few numbers, not too much, we have more or less 8 times more 3D points than any other solution, than exhaustive sieve plus exhaustive matching, because it was the real ground comparison we wanted to achieve. Pre-processing time is reduced by 42% and CPU utilization by 95%. So basically, sieve plus exhaustive matching use 95% of CPU, while we only use 4%. For deep learning techniques, it's even worse. They use like 98% of GPU, and the time taken is crazy. We also made another test with key photometry datasets. So the idea here is to know how good we can find camera position from just the video. So basically, this sequence was recorded with a camera on top of the car. The car is driving in the city. Top right, it's our resolution, and bottom left, deep learning, and bottom right, it's classic pipeline. You can see at this point that the classic pipeline do really, really bad at the beginning of the sequence, and then catch up. You can also see that we still have more 3D points, and the quality doesn't seem to be that bad, which is good. So that's what I was saying. First thing the camera does in the classical pipeline is going further away from the 3D quantile, which is real behavior. So those graphs represent the camera position, top view of the camera position. In red, you have the ground truth camera position, and in blue, you have the one computed based on the 3D reconstruction we've made for the three pipelines. Our solution in the middle. On the right, it's classic pipeline, and on the left, it's deep learning pipeline. Ideally, you want both curves to be on top of another. You want the blue one to be on top of the red one. So for that specific sequence, we do way better than classic pipeline. Not as good as deep learning technique, but still having really good results with absolute trajectory error median of 0.51 meters, which is quite good. Yeah. So, I need some slides, but I'll just say it like that. We also have metrics to compare the point cloud themselves. So chamfer distance and Hausdorff distance, which I use to say how good point cloud is. So in our case, we are working with companies in the industry who are actually using ColdMap exhaustive matching. So the idea for us is to compare to that results. And what we can say is that we actually do as good as the exhaustive matching, and sometimes we do better. Some reconstruction doesn't work with exhaustive matching, but still are working with our pipeline. So we actually did turn AV1 into a feature matching tool for high quality structural motion. The really important thing is that there's no image processing needed. So it's faster, it's cheaper, it's better, it's amazing. It unlocks new applications for edge devices computing. We are currently trying to put that on a small drone. It comes with other issues, so it's not strictly for motion anymore. It becomes SLAM, simultaneous location and mapping, so it comes with other problems. And yeah, most important part, we did reduce the time it takes to perform everything, but it's still research code written in Python, no optimization at all. I mean, no one wants to see that code, to be honest. So we are currently trying to optimize, no, not trying, we are optimizing this code, writing it apparently in assembly, if we have to listen to a FempEg Twitter accounts. And we'll try to release it later on this year. Thank you. Yes.
So when I saw the tram thing, and you then did the cover, I was wondering how would it be when it's turning. But I guess beyond that, if you have the drone, let's say the drone is like doing barrel rolls and stuff, and if you have the background moving along, and you don't have like a really clear thing as what the actual static background is, how does it handle that? Could you like draw a path through 3D space? Like only if you're in the middle of a carousel that's rotating around.
So first, the curve are currently not an issue.
Okay.
It works well. For the barrel roll, I can tell the tram wasn't doing that.
Okay.
So I haven't tested yet, but it's surely gonna be an issue. Something we've seen is that when you have a lot of motion blur, you have a high drop of motion vectors and motion vectors quality. So surely they're gonna be some kind of limitation there. But I cannot say more for now since I have no tests.
So I don't know how feasible it is, of course, even like in a plane or something, but so be able to track your motion independently of like GPS and stuff, I guess is something that could be something that would be interesting to people.
Yeah, so I mean, in order to do an efficient slam, there's a lot of data you could use. So GPS is
Why
one.
your gyroscope?
Even LiDAR technologies could be really useful. The idea here is to try to have something relying mostly on vision, to keep it really not expensive, really cheap, so it can run on consumer hardware, but not expensive consumer
That's
hardware.
cool.
Thanks. Yes.
So you showed numbers like 92% CPU reduction,
Yeah.
but I'm assuming this does not count the encoding part,
No.
which eventually, like, you have to
So-
encode. And also, did you notice any difference in the results, the quality of the results, when using different encoders with different parameters? And
So yes, so first of all, indeed, we do not count the encoding parts. Why? Because the idea here, so this work was thought with some partners we have at the university, and they had this issue like, okay, we have stored files, stored video, which are encoded, but no one cares about the fact that they're encoded because they're still processing them like, okay, the only data available is the HTTP data. So we just decided to go with, okay, there's more in it, so we're gonna reuse it. So in those numbers, we do not count the encoding part because, well, it's supposed to be already encoded. Also, you could extract motion vectors during the encoding, which will also reduce the cost of it. It's the same. So basically, all the time numbers starts right here after the encoding pass. And there's a lot to optimize. For example, extracting the metadata here is not optimized at all. So it's inspect tool from AV1, which they basically take your file, decode it, and write everything in JSON, and then you query that JSON. So that's also something that we can even more reduce things. And last part, usually when you have a drone, like you're flying a drone somewhere, you'll have the video coming to your phone. This video is encoded, so that's why we do not count the encoding parts in it. The second part of the question was?
did you notice any difference in quality when using different encoders?
Yes.
Or different
So in the paper we present in VCS, we try different presets for AV1, and we also compare it to NVA and KV1. And basically the quality of the motion vectors and something I call the motion vector coverage, so how many blocks actually have a motion vector, changed a lot. So we found out that for AV1, best speed preset was CPU6. So that's what we are using in the current pipeline. But we need to do more tests to see the impact of it, trying with SVT AV1. Probably someday with AV2, when it will take less than a year for me to get an encoded video. Okay. That's any other question? Yes.
Do you do any special handling for wedges or warp motion? And if so, did that help results?
No special handling so far. We are looking into it to have better quality at the end. So, yeah, we need to dig deeper in it. Yes.
Do you have any plans to use the motion vector units, for example, the NVIDIA motion flow?
I couldn't hear the first part of it, sorry.
Yeah, do you have any plans of using the native?
You mean NVIDIA already existing tool for getting?
No, I mean, like, for example, Vulkan allows you to expose the NVIDIA motion vector body directly, which is used by encoders and by QRF. So this would allow you to skip the encoding instead.
Yes, indeed, but it's a good option the thing is, we are trying to, like, this work is really linked to encoding process. Why? Because we are saying all your videos most of your videos are encoded, so if you work in VFX and stuff like that, but most of the videos are encoded, and it's to show people that there's more in it than just a drop in quality or whatever. And since we try to make it work on really small hardware, NVIDIA GPUs, like we did try with NVM because it was handy and it's there, but we are mostly targeting CPU work to see if we can get real time with really cheap hardware.
So the unit is exposed even on bigger parts, so we should have luck using it. But of course, that is if you are planning on using it in for example, a film or some other low power application. Yes.
It probably wouldn't work because you don't necessarily have enough points, but I guess so the like Gaussian splatting render where you got the point clouds, your one especially compared to the other ones, there's parts of it where basically you can see the image. I mean, even there's the street sign, you can basically see the text on the T-screen or whatever is next to it. So I was just thinking it might be cool to try to do that. It probably wouldn't look perfect, but
yeah, we are looking into using Gaussian splatting technology, triangle Gaussian splatting, to see the impact of having a denser point cloud, and well, how impacting it is.
Because you've got the colours as well, I noticed, where the other ones that just seem to be completely black dots.
Yeah, it's because we have more density, so it seems more colorful. But in theory, you have also colors it's not in theory, you have also colors in the seat reconstruction. It's just that it's harder to see since you have less density. Yeah. Good. Thank you very much.